Men altså, vi laver lige en poll i starten om, hvor mange der kender konsol.
Ja.
Sådan så vi kan få, sådan så vi har en idé om, okay, hvor mange der kender det.
Yes, den er klar.
Ja. Skal vi måske skifte til engelsk?
Yes, let's do that.
Yes, probably for the best. We have an international crowd today, I think.
Yeah.
Yeah.
So, minutes.
Hi to everyone who's joining. We're just going to wait a few more minutes to let people get set up before we start.
Mm-hmm.
Unless you know where the Q&A and the chat and everything is, you can.
Yeah, so I think Tua will keep track on the questions and then interrupt me and ask the questions.
That sounds good.
Yeah.
Yeah.
So I can see there's a few known names out there.
Oh yeah, I can have a look here.
Oh, and Tua, if you're writing a message, make sure you write to everyone.
Yeah, this one was specific to one person, so.
Oh, I see. Okay, sorry. I just thought it said host and panel. Wonderful. Just testing out all the features here before we get started.
We are getting close to the top of the hour.
Mm-hmm. Yes. So I know you've been doing a lot of online workshops with different focus areas, focus topics.
Yeah, it's been, well, we've always done a lot of webinars, but of course, especially the last 2 years with the pandemic, it's been exploding, so to speak. So.
Yeah, especially for you, because Mads, you are also more international than the rest of the Danish office.
Yeah.
So it's much easier if you don't have to travel every time.
Yes, for sure. But yeah, and also some of the usual customer visits have been switched to a webinar. But I hope I'm sure it will get back to like a more, what do you call it? Good distribution of physical meetings and online meetings.
Yeah. Do you also offer consultancy where you're building up?
No, we have certified consultants that we refer to. So we don't do consultancy as such. We don't want to mix it. We are a pure software company, but we do have certified consultants us within acoustics here in Denmark. So if someone is in need of help, then we can guide you to the right person.
Maybe we can include a link I don't know if you have a list of them or anything, but I'm sure that some people might be interested.
Yeah, they can just contact us with a specific problem, then we can guide it to the right consultant, so you don't have to figure out yourself which one is.
Who is the right one for the job? Excellent.
Yeah, we do. So we don't get misunderstood. We do, of course, provide support for people that use our software. So but we don't do consultancy per se. So we help people when they are using the software.
Yeah, I see.
Should we? Yeah,
let's get started. We can see that some more people have joined now. Welcome everyone. See, there's quite a lot of people from around the world, which is nice to see. Today we have a webinar together with COMSOL, and the idea is to have 2 parts, where the first part is a presentation, more of a webinar format, and the second part is a web workshop, which is more hands-on, practical. Perhaps we can just start with introducing our 2 guests. We have Tor Ralphs, who is the director of COMSOL Denmark, and we have Mads Herring Jensen, who is the the technical manager of acoustic products at COMSOL as well. And he's doing a lot of these online webinars, helping people get started with COMSOL. We wanted to check with you, first of all, if you had ever used COMSOL before. So I'm going to launch a poll, and you can, hopefully you should be able to see it right now. That's a lot of yeses. Can you see the results already?
No.
No, okay, you have to wait until the end. It's exciting. I can see them. Yes, that's everyone has finished it now. Okay, so we have 81% of people here have used COMSOL before. So you don't need to start from the very basics, perhaps. Yeah, and oh yeah, a couple of practical things. We have a Q&A chat here at the bottom and a regular chat. So if you just have a comment or feedback, you can write it in the chat, and if you have a question along the way, then write it in the Q&A chat. And we really recommend that you make use of that, and don't feel that any question is stupid, or if you're confused along the way, then please write in the Q&A chat, because you're going to get a lot more out of this if you're involved. Great. Then I think I will just hand over to Mads and Tor to get started.
Great. Yeah, thank you, Shelley. I can just, you already introduced us. Yeah, my name is Mads, and I'm the technology manager for the acoustics products at COMSOL, and I've worked with COMSOL for 11 years actually this month. Tor, you are helping me out here during the webinar part. You'll be reading out the questions, but you can also maybe introduce yourself.
Yeah, my name is Tor, and I've been with COMSOL for 25 years, so it's quite some time now. And I will do the web workshop, but with 81% actually knowing COMSOL beforehand. The workshop part will maybe be a little less. Maybe we should focus more on your part, Mads. And then for those who haven't used COMSOL so much before, we will build a simple model including some of these thermoviscous losses that it's all about.
Yeah, sounds good. Of course, also during the presentation, if you see anything during the day that you would like more information about, please contact us. Could be me referring to a specific simulation model or tutorial or something that you cannot find. Please get in contact with us. And I also want to reiterate that you should, of course, ask a lot of questions in the Q&A tab here in Zoom. And Tor, you'll be reading them out to me, I think, and we'll take questions along the way. And then at the end, we'll also, of course, have time to more questions if you come up with more questions. Yeah. Sorry. So let's get going. So today I want to introduce you to the most important concepts related to thermoviscous acoustics, or they're also sometimes called microacoustics. And it's an important phenomena that is sometimes, I think, or just hidden away, so to speak, as acoustic losses. But why? What are they actually? This is something I want to try to answer today. And also, my point today will also be that you can actually model these losses in great detail, and you can gain a lot of insight using simulation to model thermoviscous acoustics. So I will have a short introduction. What is microacoustics? Then I'll be focusing on a few examples. I will actually start with a Helmholtz resonator model with a lossy neck, so to speak. I'll talk a bit about perforated plates. Then we'll see some more advanced applications like microspeakers, microphones, hearing aids. So in all these examples that I mentioned here, we have small length scales in this millimeter and sub-millimeter range, and that's why we sometimes call it microacoustics. Then we will have a bit of theory today. So I think it's good to sort of just get an idea of where the governing equations are coming from. And then I have more examples prepared, advanced topics, and I'll be mentioning nonlinear effects also. So actually the image to the right here is a model of an Ole Wulff microspeaker. And the image, yeah, is some nice colors here, but this is an actual tutorial model we have of an actual microspeaker. And now that I mentioned nonlinear effects, I just want to show you a cool animation of something that is also a thermoviscous phenomenon. Is actually the generation of, in this case, thermal waves or thermal vortices, where when you have a high intensity acoustic wave interacting with a small slit. So this is a much more advanced topic. So it's nonlinear transient simulations, but the colors you see here is actually temperature fluctuations of the acoustic field. So just to, it's a nice animation with some nice colors also. Good. So what is microacoustics? I would define it, or it's defined as acoustics where the characteristic geometric length scales are comparable to or smaller than the thermal and viscous boundary layers. And the thermal and viscous boundary layer thicknesses, we'll get back to those, are typically in the range smaller than millimeters for air, and even smaller for fluid or liquids like water. So that's why we call it microacoustics, because it's acoustics where you have millimeter length scales. So thermoviscous acoustics, as we like to call them, which maybe more refers to the physics going on, is also sometimes known as viscothermal acoustics. We call it thermoviscous acoustics. Some people also refer to it as linearized Navier-Stokes, but that is very specific to the equation solved, and it's not always the case here. We are not always solving the linearized Navier-Stokes equations to model thermoviscous effects. As we will see, we have some other methods that will actually include these losses without having to solve that specific equation. I also want to mention that the thermal and the viscous boundary layers are sometimes called the thermal and the viscous penetration depth, if you've heard those expressions before. Let's have a look now at what is actually going on when you have an acoustic wave propagating. So this nice animation here shows you in color a pressure wave that travels down a pipe, and then with the pipe or with the dots is actually highly exaggerated. You see the movement of the air. So when the pressure wave is propagating, the air is locally moving back and forth. So if you follow one of the thicker dots, you can see that the air is moving back and forth, while the pressure wave travels downstream. So here we are it could be a big, thick pipe. And now we will zoom in at what happens near the wall. So the little zoom box here. So now we've zoomed in, and we still see in the bulk of the fluid, we see the big dots moving back and forth. And what I've then done is that I've added some extra dots near the boundary. So at a wall, a solid wall, when you have the air moving back and forth, on the wall itself, the air is not actually moving, it's sticking. So we have what is called a no-slip boundary condition. And in the transition from the air not moving at the boundary to the air moving back and forth in the bulk of the fluid, we have what is called the viscous boundary layer. So you can see with the small dots, you can see this is this transition from regular so to speak, movement to this no slip. And it's within this, so the thickness of this layer is called, this layer is called the viscous boundary layer. And the thickness depends on the excitation frequency. I've put one number here. So at 100 Hertz in air, the thickness is around 0.22 millimeters. So that's what I meant with this millimeter size, or why we call it microacoustics. So what happens when you have this change from the uniform motion to the no-slip motion at the wall is you have big changes in the velocity, big changes in the particle movement. And when you have big changes, you have gradients in the velocity. And when you have gradients in the velocity, you get a lot of viscous dissipation. You get a lot of losses. So it's within these thin boundary layers that you get a lot of, or you get all the losses that we are talking about today. So, yes. So, I also want to mention that I'll come back to this a bit later, but associated with a wall, there's also something called a thermal boundary layer, which has to do with temperature fluctuations. We'll see that a bit more in detail later on. So you've heard me saying this a few times, dissipation. So when you're modeling these devices with the small length scales, you get an important effect, which is dissipation, viscous and thermal dissipation. And where does that happen? Well, it happens where you have narrow regions, where you have cross-section jumps from a thick to a thin pipe. For example, on the image to the right, you have a few examples where you see these dissipations, these losses being important. At the bottom, you have a perforated plate that are used for sound control. At the top, you have a mesh, could be a mesh in front of a loudspeaker, for example. And the colors here represent the amplitude of the velocity, the fluctuation of the movement, back and forth movement of the air. And when you see the changes in the color from the red to the blue, that's where you have all the losses. There's also another effect that you can capture when you model your acoustics using the governing equations that we will get back to when you model acoustics with more detail, and that's the ability to capture the transition from adiabatic to isothermal behavior. So this is an effect that you typically see at low frequencies when you have closed volumes, for example, in microphones. So the image to the right is a section of a condenser microphone. And what you see with the colors is the amplitude of the temperature fluctuations inside of the microphone. So I've put here with small arrows, this is like the thickness of what is called the thermal boundary layer. And actually what happens is that these layers that I mentioned, they are actually growing when the frequency goes down. So imagine that you have a boundary layer that has suddenly the same length scale as your whole geometry. Then suddenly your temperature fluctuations go to 0 in the full volume, and then you actually get isothermal behavior in your fluid. And when you get isothermal behavior in the fluid, that actually changes the compressibility of the fluid and the effective speed of sound in the fluid. I've added some numbers here to the left. So the relation between the isothermal speed of sound and the adiabatic speed of sound is this 1 over square root of gamma. So in air, the adiabatic speed of sound is 345 meters per second, say, and you'll have the isothermal speed of sound, which is only 292 meters per second. So at very low frequencies with small volumes, you actually effectively change the speed of sound and the compressibility, which is important, particularly to capture when you model microphones. So these effects are all associated with what we call thermoviscous acoustics. And when you model in great detail, you will actually capture the full transition from isothermal to adiabatic. So there's, of course, a smooth transition from the two behaviors. Good. So that was the first.
A quick question,
Yes,
Mads.
sure.
These models that you showed, are they available on and also the 3D speaker mesh model? Are they?
Yes. Yes, sure. Nearly all the models that I'll be showing today are models that you can find on our homepage, or if you are already a COMSOL user, they'll be in what we call the application library. So they are tutorial models that you can download. We have documentation for them that explains you the details of the setup, etc. If you're not an existing COMSOL user, but you still want to have a look at some of these models, you can search for them on our homepage. So you can, for example, search for a microphone, and then you'll get a lot of the models popping up. And you can always download, I think, the documentation for the models. There's a PDF file with explanation. Some of the models that I'll be showing today have actually modified existing models to sort of show a point. And if it's a model you would like to have, please send us an email and I'm happy to send them. So let's go on and look at a few examples. So the first one, I will be looking at a Helmholtz resonator. That's, I think, a system that we all know if we've been studying acoustics. Then I'll be looking at a perforated plate, an ear canal simulator. Then I'll be showing some examples of microspeakers and also a compression driver example. Good. So first, let's look at a Helmholtz resonator with a narrow neck. So the geometry is shown to the left. And you have a resonating volume V, you have a neck length L, and you have a cross-section area S. And then if you set up a simple lumped element for this system, where there are no losses in the neck, then you can compute the resonance frequency given by the expression below here. So this is the lossless formula. In the image to the right, I have shown the response of the system for different radii of the neck. So 1 millimeter, 2 millimeter, 3 millimeters, etc., etc. So in the graph, you have the vertical dashed lines. Those represent these resonance frequencies for the different radii. With the dotted curves, you see the lossless response of the system, so the system without any losses. And then with the full curves, you see the actual response of such a Helmholtz resonator, where you include the thermoviscous losses in the little neck up here. So what you see is that for the smaller radii, you get a very good agreement between the analytical expression for the resonance frequency and the actual resonance frequency when you have no losses. And yeah, the smaller the neck, the better the lumped representation of the model, where there's actually no compliance taken into account in the little neck here. So as the neck gets larger, the effect of the compliance of the air in the neck gets a bit larger, and you see a small deviation from the analytical to the actual response of the system. Also, don't mind that the peaks here are, some of them are high and some of them are small. When it's a lossless system, the peak is infinite. So the peak here just should actually go to infinity, but we only have a limited resolution. But what is important or interesting to see, I think, is that when you include losses in the neck, which are of course there when you have a real system, then you see the classical behavior where you get a lower resonance frequency compared to the lossless, and you get, of course, a much lower resonance amplitude. So this is, of course, a simple textbook example. But many actual systems that you have out in the world have this Helmholtz resonator behavior, where you have certain components in your system that actually make up a resonator, Helmholtz resonator. And when you have small dimensions, then you need to include the losses to capture the resonance peaks and resonance behavior of these subsystems correctly. I think I will actually, since there are so many COMSOL users present today, let me open the model that I set up in COMSOL. I will not go through the details of the setup. Tua will be doing that, not on this particular model, but after this presentation. So this is a very simple setup. There's a very simple geometry. It's a 2D axisymmetric model. And I've parameterized my geometry here. So the radius, the length of the neck, the radius of the volume here, the height of the volume. And then I've included the losses in this case. This is something I'll get back to. I've included the losses in the neck here using one of our many formulations, which is called the narrow region acoustics. And this is, so the losses are included in the neck only in this model. And then I've solved the model with and without the losses. And you can see, you can change the neck size here, for example. You can, of course, post-process everything you like, and I've made a plot here of the response. So I'm just probing some pressure level somewhere in the resonance volume. Any questions so far on this? No?
No, not
good.
Not yet.
Not yet. Please ask questions. So yeah, again, this was a very simple, small, classical textbook example, but I think it shows what you actually see in many systems. So one classical Helmholtz resonator system is the ear, where you have, when you have an earbud or a hearing aid coupled to the ear, you actually have a Helmholtz resonator in the ear. And this is typically what you see. You see the resonance. If you change, for example, some tube diameters connecting to the ear, you see typically that you get a lower resonance frequency, and you lower the amplitude of the resonance. So it has some actual applications. I also know, of course, that you can, I mean, there exists, so for this, if you have a circular duct and a nice volume, you can add corrections to the analytical expression that will take the losses into account to some extent. But that's only, of course, true if you have a circular duct and a very simple geometry. As soon as you start building something real, you can do some approximations, but if you want to capture the losses correctly, then you need to use simulation. Good. My next example here is perforated plates. So I want to mention this example here we don't have in the library, but if you want it, we'll be happy to send it along. Next, we'll be looking at a perforated plate. And as you probably know, perforated plates, they're used for sound control and like wall panels, if you do sound insulation in buildings, but also the concept of perforations are used in many transducer applications like microphones. And by controlling the perforation size and shape, you can control the vibration behavior in your devices. So perforated plates or micro perforated plates are very important concepts in acoustics. Again, analytical models exist for uniform, like perforates, where you have uniform distributions of the holes, like you see in the image below here. But there's typically in the analytical models, you always have some tuning parameter, and you may recognize some of them if you work with these. So it's like the end correction length or the whole interaction function that you actually use to have for these analytical or semi-analytical models. But with simulation, you can actually model a perforated plate of any shape and any design really efficiently. So let's first have a look at the images here. So they are taken from our tutorial model directly. So the image to the left shows you the transfer impedance of the perforated plate. And I think in this setup, the plate is 1 millimeter thick and the whole radius is 0.3 millimeters. And the graph here shows the real, imaginary, and absolute value of the transfer impedance. And in blue, you have the COMSOL model, and in red, you have this classical semi-analytical model. And we see there's a nice and relatively good agreement between the analytical and the simulation results, which we of course also expect. But now say your perforations are not straight cylinders, but actually maybe have a conical behavior. So what I've done is that I've changed the geometry here from being a cylinder to actually being a cone connecting the two surfaces. Could be when you build the holes or you drill the holes, or the technique you're using, you actually get conical behavior. It could also be that there's some design engineer that thinks it looks more beautiful when your plate in front of the speaker has some nice shape for the perforations. Then suddenly the analytical models stop working. So for this shape here, I'm again comparing the analytical model, and in this case I've made maybe a very simple assumption, but I've put the effective radius of my cone to be the average of the inlet thickness and the outlet thickness. And that's maybe not such a fantastic, could probably be made better, but anyways, there's no good expression for this. And you see now we suddenly see a large deviation between the analytical and the simulation. I can actually animate the thing here, but you see a larger deviation. And note that on the left-hand side, it's the logarithmic scale.
Yes, these things are all geometry dependent, and there's a question about if these losses can be level dependent.
Yes.
Also, and will a frequency study actually capture that?
No. When you model in the frequency domain, you are always modeling linear phenomena. But we actually have, and I'll be showing that later during this presentation, and we have a tutorial model on our homepage where we actually compute the transfer impedance of a perforated plate using, we have something called nonlinear thermoviscous acoustics, and you need to jump to the time domain and to include nonlinear effects to capture these level dependent behavior, so nonlinear behavior. So we actually have a tutorial model that shows how you model these effects. It's a good question.
Yeah, and the next question, of course, is when you now have these impedance, how do you then use them in a large 3D model where you actually don't draw the holes, but then you have a impedance boundary condition, right?
Yes, that's a good, yeah. So it's a very good point too. So say you had could be a muffler system, for example, where you have a lot of perforations in, and your perforations are not standard circular holes, but they have maybe a strange shape, or maybe they are rectangular or whatever. Then you make a submodel like this one. And you can actually see here that I'm only modeling a quarter of the hole, so you can use symmetries. And then what you do is that you extract the transfer impedance, so the real and imaginary part, and then you can, in your system simulation, so when you actually start to model the whole muffler, then instead of drawing all the holes, you add a transfer impedance boundary condition, and you use the computed values in your larger system simulation. So I think it's important to break down large complex models to use computational power, detailed models like thermoviscous acoustics to model, for example, perforations with great detail. And then when you jump to do your full system simulation, you use the results, the output of your submodels, for example, computing a transfer impedance.
Yeah, and on the topic of computing the transfer impedance, I can see we have it must be a user of console. He's asking why we are calculating that as at the middle of the perforate instead of having a volume average on the domain.
That's a good question. You could add that. Well, for the circular duct, straight duct, I don't think it will change probably the results, but could be that actually it's a better metric when you set up if you have a conical hole perforation, it's a good question. It's a good. Yeah, we can try. It's a good suggestion.
We can try that when we are done with this webinar to see if it makes a difference and let you know.
And it's good. Two, you'll remember that, right? So I don't forget to look at it. Yeah. Where was I? Yes. Yeah. I can maybe, since I built the model, let me just open it here. So this is the model. So what I'm actually modeling is only a quarter. And this model is nice because it's parameterized, so it's easy to change some of the parameters. So I have the top radius and the bottom radius and the thickness of the plate, the distance in the X and Y direction. So by changing these parameters, I can easily change this, like how my hole is looking. And you're right, in this model, the transfer impedance is computed by looking at the average velocity in the middle of the hole. I don't know if the results will change much, but could be. So then you can, of course, look again, post-process, you can look at the velocity. So what is nice also, I think, so if you've worked with perforated plate models, you remember there's this concept of end correction. And what it is that, so the color here represents the movement of the air, right? And the end correction is actually, since the air is moving in the duct or the perforation, some air is actually also moving outside of the perforation. And the length here, sort of the effective length of this piece of air moving out here is actually the end correction. And we've looked at this for some conference papers before, and you should actually use different end corrections for the resistive and the reactive part of your transfer impedance, which is typically not used in the analytical models, but it's something you can play with when you have these detailed models. You can also see the temperature fluctuation in the model here, and then the transfer impedance. We've also computed stuff like surface normal impedance and also the absorption coefficient. Yeah, and then we've used some post-processing tricks with some mirror data sets to make it look like we modeled 4 holes actually. Post-processing, it's a whole story. Good. Yeah. Another example that many of you may recognize is the model of an ear canal simulator. So that's a standardized volume that will mimic the acoustics of the ear when you, for example, for testing earbuds or something like that, or hearing aids. And we have a model of an older coupler, which is sometimes known as the 711 coupler. And in this model, you have, so this is actually one of the tutorial models tour you will be showing in the hands-on session. Yeah.
We'll play a little around with that.
Yeah. So you have a central volume, and then you have, which represents the volume of the occluded ear. And then you have the side volumes and some very narrow slits that are actually there to introduce the losses associated with the eardrum. So you want to mimic those using an acoustic system. And the image to the left here shows the transfer impedance. So in red, you have the standard IEC curve. In blue, you have the transfer impedance computed with this geometry. And then in green, you have the transfer impedance computed if you don't include the losses in these narrow slits. So obviously, it's very obvious in this model, if you don't include the thermal and viscous dissipation, then you will not get a correct response in your simulation, and you would get completely wrong results. I want to mention that the most narrow of the slits here has a thickness or height of 7 micrometers, I believe, only. The other one is 100 something micrometers. Yeah, losses are important. Good. Time is flying.
I have plenty of time.
Good. So now let's move more to less maybe theoretical or academic examples, to some examples of actual applications. So again, to motivate the use of thermoviscous acoustics. So in this case, it's a mobile microspeaker and a mobile device. So you can see the large system on the left here. So you have a small microspeaker in this enclosed volume, and then you have the port of the microspeaker. And then the colors on the left here, the lines, is the intensity curve, and then you have the pressure distribution below here. I think it's at 4 kilohertz, or it's at 3 kilohertz. And then I've made a zoom on the port on the left, and again you recognize, actually in this model you get a lot of effects going on. So you have a small closed volume where in itself you have losses, and you have actually also these change in compressibility at the low frequencies because this isothermal adiabatic behavior. And then you actually also see in the port themselves you have losses going on. So this is a model that includes a transducer modeling, and it includes thermoviscous acoustics in the vicinity of this model and the port, and then we couple it to pressure acoustics outside. So as soon as you're outside, when you don't have any closed volumes or small dimensions, then you can use regular pressure acoustics, and you can couple the two. So you sort of use, we'll see that, but the full thermoviscous models are more expensive to solve than regular pressure acoustics. So you want to use your computational power where necessary. There was this question about nonlinear effects, and actually we have a version of this model that is solved in the time domain. And what you see is that you actually get some, when you start to use your, or play or use your mobile phone and play at high SPLs, high amplitudes, then you actually start to generate small vortices at the outlet here, at the outlet ports. And those lead to extra resistive losses, but they actually also lead to distortion. So you get harmonic generation. As soon as you have a nonlinear phenomena, you will get some harmonic generation. So that you can model also. It's in the more advanced category of simulations. Good. Yes, then this is the image we actually saw in the beginning, and the image you have in your background tour. It's a full multiphysics model of a small microtransducer. So this is an Ole Wulff microspeaker, and it's the actual geometry that we have received from Ole Wulff, and we have measurements and material data from them. It's one of our tutorial models. And this speaker is, I think the number is actually, so it's 19 millimeters in diameter, if I'm not mistaken. And that's a full electrovibroacoustic model where you have moving parts, you have thermoviscous acoustics in the back volume of this, you have some thin slits. Maybe it's a good idea to open the model so you can just see in COMSOL. I mentioned these. If you are a COMSOL user, you will probably know this, but we have this application libraries, acoustics module, electroacoustics transducers, and this is the Ole Wulff microspeaker.
Maybe just nothing to do with acoustics at all, but yeah. The picture behind me is completely created in COMSOL, so you can do nice post-processing. Yeah, especially in the.
It's. Yeah, you can see it's a complex geometry where certainly, I wonder if there's some good plots here, where certainly, you know, using any analytical models would be very challenging. So you have these slits here that connect the back volume of the speaker to the outside. You have the mechanical movement of the membrane, speaker membrane, and it's a fully coupled model here. So quite an advanced model, very nice model, and it shows, you know, you can then compare measurements with simulations, and you get some very nice agreement between the measurements and the simulations. And again, we actually in this model show the difference between including and not including thermoviscous losses. Total impedance measurements, etc. So this is the electrical impedance. And we're actually doing some, just to say a few words about this model, we're doing some, again, this sub-modeling tool that we talked about in this model, we're actually analyzing the electromagnetic system separately, and then extracting some lumped models that we're using in a small electrical circuit to represent the electromagnetic part of the problem just using a electrical circuit. And then for the 3D model, we are only, so to speak, modeling the structural and the acoustics with full fine element simulations.
I think the nice part of this one is also that it shows you that you can do part of the model in 2D and part of the model in 3D.
Yeah.
So always use your computational powers as efficient as possible.
Yes, definitely. And if you are also, just to get back to the application libraries, one thing is opening the model, but there's also a nice documentation down here. So you can open a PDF with first a long description of the model or longer, and then also step-by-step instructions if you want to follow all the instructions. So for this type of model here, they are very long, but you know, we have some nice introduction tutorials. Good.
I'll show a few of those.
Yeah. So final example. Now we are moving to something a bit bigger. It's a compression driver. So I just have a few images to show you here, but here you have a very thin space. So it's a compression driver. It's a type of speaker where the diaphragm is not radiating directly into free space, but you're using a phase plug that is fitted very closely to the diaphragm to connect the diaphragm to a waveguide that is sending the sound out. So the diaphragm is up here, you have a thin region, you have the phase plug, and then you have a waveguide in this case. So this system includes narrow regions between the diaphragm and the back plate, or the front plate, I think it might be called, but you also have thermoviscous losses in these in the phase plug here. So if you want to model compression drivers correctly, you need again to include thermoviscous losses. And then we have a model. This is actually a model that you cannot find on our homepage, but we are happy to send, where we are actually where the driver membrane of in my compression driver is actually modeled with a composite material. So in each of these squares here, you have a different orientation of the fibers in the speaker diaphragm, which generates this interestingly looking SPL distribution in the model. And you see, you get some strange like deformations in the membrane because it has these composite properties. Yeah.
But this is a different size except for the thin membrane. So again, just maybe a few words on when these losses should be included. One thing is that the small dimensions compared to the frequency, I guess, or whatever. But also, I don't think we touched that completely. The level, if you have something and you turn up the volume, these losses become more severe.
So, well, they are linearly proportional with the level. So, or if you model it in the frequency domain, then it's just a linear relation between the level and the losses. The losses depend on the frequency. So the higher the frequency, the smaller the losses. The lower the frequency, the higher the losses. but the losses in reality will also be level dependent. So the higher the level, the losses will actually grow more, because you start to get typically vortex generation so those are what is called local nonlinear effects, and not global nonlinear effects or cumulative nonlinear effects. And we have a few examples that show this. But if you want to have these level dependent losses into your model, you need to model that in the time domain. But you can do that, and have some examples showing that at the end.
Okay, great.
Yeah. Good. So I think it was a long introduction, but I wanted to give you some ideas of some applications where the thermoviscous losses are important, and where you should definitely include them if you want to model your systems correctly. Now I think I will actually do a bit of theory, which I don't that often do in my webinars because we don't have that much time, but today we have a lot of time. So no, I want to sketch out where the governing equations for thermoviscous acoustics come from. So what is important is not to follow everything in detail. I will not explain every single term in the equations that I'll be showing. If you want to read more in detail, I suggest you follow the link that I think we'll send out the slides later on, and you can click on this. We have a ComSol Cyclopedia page with an introduction to acoustics, where the governing equations are sort of derived in great detail and explained. So if you think it's interesting, then I highly recommend you go look at our Cyclopedia page. But what I want to show you in the next few slides here is that the governing equations for thermoviscous acoustics are simply, so to speak, a stage before classical acoustics, before the classical Helmholtz equation. So one less simplification of the equations is where you actually get the governing equations for thermoviscous acoustics. So physically, they represent one approximation less than when deriving the governing equation for classical acoustics. And don't worry also when you are modeling with ComSol, when you're building models with ComSol, when you're running your simulations, all these equations are handled for you by ComSol. So you don't need to, type them in or anything like that. But
on the other hand, if you're a researcher and want to go into them, you can always change and manipulate the equations, right?
Yes.
So there's no mathematical black box here. It's actually all in the open.
Yes. So the equations that we have implemented, you can turn on some option and you can see them, and you can edit them if you want to do that, definitely. But yeah, for most, I think if you're working on engineering applications, you will probably not change them. Good. So let's go back all the way. The governing equations for the propagation of acoustic waves. Acoustic waves are compressible waves of small acoustic perturbations. And they are governed by conservation, the conservation laws of continuum mechanics, mass conservation, momentum conservation, energy conservation, and then a number of constitutive relations. So equation of state, relating pressure, temperature, and density, the Fourier heat law for the heat losses, and then also an expression for the stress tensor to give you the viscous losses. And you can actually see that. So pressure, temperature, density, and velocity fluctuations are all linked to each other. And we've seen that in some of my previous slides, where you could see the movement of the air in the small, narrow regions, etc. But we can just look at a pressure wave that propagates in a straight duct. At the bottom, you have a 1 Pascal. Sorry, I was moving the what do you call the video thing? So at the bottom, you have the pressure fluctuations associated with a 1 Pascal amplitude pressure wave. And as that pressure wave propagates, you can see you have velocity fluctuations that are on the scope of millimeters per second. And you actually also associated with that have a temperature wave that propagates. So you don't often think about that, but when a pressure wave propagates, you have a small temperature wave that propagates. But here we're only talking millikelvin in this case. So it's not something you don't experience that, but these things are just all coupled together. And typically when we talk about acoustics, we just look at the pressure, of course. And we'll see why now. So, good. Governing equations of continuum mechanics, they are stated here. So mass, momentum, energy conservation, the first three equations, and then we have the equations of state, Fourier heat law, the stress tensor expression, and the equation of state. And what you then do to compute acoustic governing equations is you take these equations and then you insert a small perturbation. So when a pressure wave is propagating, it's a small pressure fluctuation around the background pressure of 1 atmosphere. In the same way, the temperature fluctuations is a small fluctuation around the background temperature of 20 degrees, etc. So you insert a perturbation of the dependent variables in the following manner. Very simply put, you say for example, if you look at the line here, my total pressure is the background pressure plus the acoustic pressure. So I'm using a subscript 1 here to represent acoustic pressure. If you look at the top right here, some people add a little prime, some people add a subscript 1, some people don't add anything, but it's now the acoustic pressure. When it's not the acoustic pressure, there's a little 0, so 1 atmosphere background pressure. If you go to the frequency domain, you assume harmonic variation of all the fields. So you are only solving one frequency at a time. You see that the frequency enters explicitly here. You're looking at one Fourier component at the time. You take these expressions and then you plug them into the governing equations that you solved before, and then you only retain all the linear terms to get linear acoustics. So we are plugging in the stuff to the right here. And linear acoustics, before we go on, these are the assumptions or the conditions that should be fulfilled for linear acoustics to be valid. Your velocity fluctuations should be much smaller than speed of sound. The density fluctuations should be much smaller than the density of air, 1.2 kilogram per cubic meter. And your pressure fluctuations, you can actually compute that they should be much smaller than this expression here. So these, if those are fulfilled, you have linear acoustics. Good. When you plug these things in and collect all the terms, you rearrange, you throw away terms, then you get the general compressible thermal equations that govern a thermoviscous acoustic fluid. So these equations here are what we solve when we solve a model using thermoviscous acoustics. So we solve these three equations here. And what you'll see is that we solve for both velocity fluctuation, pressure fluctuation, and also temperature fluctuation. So you actually solve, and in 3 dimensions, you have 3 components of the velocity. So we solve for 5 fields. So remember that it's important. So this sort of hints that this is more expensive than when you just solve for the pressure. So these are, they describe, when you solve these equations, they will capture all these phenomena that I've shown you, like the acoustic boundary layer, the thermal boundary layer, the transition from isothermal to adiabatic behavior. All these things are captured with these equations. So I just want to show you how you come from these equations to the Helmholtz equation. So what you do is that you remove all the losses explicitly. So you set viscosity and thermal conductivity equal to 0. Then you get the 2 equations to the left. Then you take the divergence of one equation and insert it into the other equation. And what you get is Helmholtz equation, which is the classical equation that we typically learn about in acoustics classes. So it's not, the equations don't, come out of thin air. It's actually the same equations we solve, but just at different levels of approximation. Just want to mention that you can if you have the Helmholtz equation and you want to introduce losses into it, what you can do is you can define a complex valued speed of sound and density. And this is something we use a lot in our what we call equivalent fluid models to mimic all kind of losses in pressure acoustics. You can also see that if you have solved for the pressure with Helmholtz equation, you can actually recover all the fields that we had before. So the velocity has to do with the gradient of the pressure. The temperature is related directly to the pressure with some material properties. And the density fluctuations are related directly to the pressure fluctuations through the speed of sound squared here. So this is the linear adiabatic equation of state. Good. That was quick. Was it okay, Tua? Good.
Yes, that's fine.
Yes?
There's a question.
Yeah.
Someone is asking. It all seems to be related to something very close to the boundary. Couldn't it be a boundary condition? Just.
Yes, that's a very good question, and I will actually come back to that. So I want to mention that this boundary layer, as I showed you in the beginning, was, for example, actually, next slide. In the middle here, we see the thickness of the boundary layer at 100 hertz is 0.22 millimeters. And at 1 kilohertz is 0.07 millimeters in air, and you can see they're even thinner in water. So if you have geometry details that are comparable to this, so maybe you have a slit, like the 711 coupler had a slit that was 70 micrometers, then the boundary layer is everything. So then you cannot really talk about what is boundary layer and what is not boundary layer. Then everything is the boundary layer. But if you have a larger model, maybe a pipe that is 3 millimeters in diameter, then definitely, and I will actually show that you can actually model what happens in the boundary layer just with the boundary condition. So it's a good point. So in this slide, I have some numbers for you. So to the left, we see it's a sketch of a wave moving from the bottom to the top or upwards. There's a wall at the right. It's isothermal and no slip. And then you can see the two curves here represent the amplitude of the temperature fluctuations and the velocity fluctuations. And this is in an air system. And in the air, the thickness of the thermal boundary layer and the viscous boundary layer are roughly the same. So the last equation here relates thickness of the thermal and the viscous boundary layers in the square root of this Prandtl number here. It's some material properties. And in air, you can see it's roughly 1. The square root of 0.07 is roughly 1. Whereas in water, the viscous boundary layer will be 3-4 times thicker than the thermal boundary layer. Some colors again. The background color represents the temperature fluctuations and the arrows, the velocity fluctuations. But so just to have some numbers in mind, and again in water, because the material properties change, the viscous and thermal boundary layers become much smaller, much thinner. So I hope at least this gave you just a quick impression of the equations we solve and where they come from. And then, of course, to model all these effects, you have a lot of different tools, or we offer a lot of different tools in COMSOL. It was a good point. If the boundary layer is very thin, can this be collapsed to a boundary condition? Yes, it can. So in many situations, you have more simplified methods than actually solving for pressure, velocity, and pressure. And let's have a look at a few of those options. So the losses, I'm actually just reading here what it says. The losses modeled through the equations we just saw can be included in virtual models and simulations in many different ways, using different degrees of approximation. And that's what I was trying to say in the beginning when I defined microacoustics, is that some people like to talk about us solving the linearized Navier-Stokes equations, which is like, but to include the losses, you don't necessarily need to solve the linearized Navier-Stokes equations. You can do that in better ways or simplified ways. So the simulation engineer has a lot of choices in COMSOL multiphysics on how to include the losses. You have the faster and slightly less accurate methods. I'll come back to those. They can be very accurate in some situations, and in some situations they may be less accurate, but they'll give you faster results, and you can maybe use it for first setting up your first model to see, am I in the ballpark? This idea I had about making the neck of my resonator longer, will it actually affect the response of my system as I expect? And then you can also use a much slower and more detailed method where you get high fidelity results, but it's more expensive. And then, as we've seen also in some of the examples, these things can be coupled. So you want to do multiphysics simulations typically when you have transducers, so you can couple to vibrating solids, vibroacoustics. You can couple to classical pressure acoustics, so like in the mobile device. So outside of the small regions, you want to use just pressure acoustics. And you can also, of course, include electromagnetic forces. So we offer 3 ways to model these in COMSOL. So you can either solve the full set of equations. So where you solve, so I've shown this in the bottom here, for pressure, velocity, and temperature. So you solve for the full linearized governing equations. They are valid in any geometry and any dimension. They are valid in the full frequency range. They are computationally more expensive, but you can actually model things like complex micro perforated plates, strange geometries inside of mobile devices, anything you like, volumes in condenser microphones. And in the time domain, you can include nonlinear effects with these methods. Then you have 2 ways to simplify things, and they're actually only valid in the frequency domain, so in the linear region. So we have something called narrow region acoustics. So if you first look at the sketch at the bottom here, on the left, we see what is the actual behavior. So you have the velocity profile to some extent. You have a lot of the losses in this orange region. And then what you do is you take all the losses and you homogenize them and you smear them out over the cross-section of your waveguide. And then you actually only solve for the pressure. So that's an option. And that's also this functionality tool will show you when he models or sets up the model for the 711 coupler. So when you have a waveguide of constant cross-section, you can use this functionality called narrow region acoustics. And it's valid for constant cross-sections of your waveguides. It's valid in the full frequency range. And it's an exact analytical solution to the problem in these waveguides. And it's most accurate when your waveguides are longer than the radius of the waveguide. So if you have a very short waveguide, remember we talked about these end correction, end effects, those will not be captured because we only smear the losses inside of the waveguide itself. That's one very good method for modeling. The other one is this collapse of the boundary condition. Again, if you look at the image at the bottom right here, if your boundary layers are not overlapping, you can actually take the losses that happen in the boundary layer and collapse them to a boundary condition. And that's a boundary condition that we call, or that's called thermoviscous boundary layer impedance. So it's typically used for slightly larger structures where the boundary layers are not overlapping. So it's sort of an analytical integration through the boundary layer and collapsing the losses to a boundary condition. This boundary condition is also valid on curved surfaces. So you don't need to have a waveguide of constant cross-section. So 2 simpler methods that are both available in COMSOL. Maybe I can, yeah. And I think Tua, you will show the narrow region acoustics feature, right?
Yes.
Yeah.
For those who haven't used COMSOL and want to join the workshop part, that will work.
So I'm just jumping back here at my Ole Wulff speaker model. I just want to show you. So when you right click, you will show this also too. We have the list here, and it's called Narrow Region Acoustics. It's a domain feature, so you click on the waveguide itself, and then we have the boundary condition down here, thermoviscous boundary layer impedance, which is the other option for when the boundary layer is thin relative to the geometry. So again, the choice here is up to the simulation engineer. We have some guidelines for when you can use the different methods, but I think, again, when you test new concepts, when you are setting up the model of a system for the first time, try to use some of these more simplified, like the narrow region acoustics feature or the thermoviscous boundary layer impedance functionality. Try to use those, maybe even if you are, on the border of when they are valid, because you will be able to solve your model much faster, and you will be able to see if your design is moving in the correct direction. So you will, let's say you will maybe capture 90% of the losses instead of having no losses at all. So it's much better than not including these losses. And then when you are closer to your final design, you can start to use the full thermoviscous acoustic formulation. Of course, there's situations if you have a closed volume in a small MEMS speaker or a small MEMS or in a condenser microphone, these simplified approaches do not apply. Then you will need the full formulation.
Yeah, but it plays into this overall theme that we have talked about, using the power where you need it and using the right tool to get the job done, right?
Yeah. So. Yes. So what I've prepared now is I want to show you a bunch of more examples. I will not spend too much time on them. They are examples that you can download from our homepage, and they're all, I think most of them are examples you can download. They are on our homepage or in the software itself. And then I just want to spend a bit more time on some of the nonlinear effects at the end. And I think we should have some time for some questions. But yeah, let's see at some of my more examples here. So we're lucky to have several models that are actually built together with industry, and this is another model here. This is a model of a so-called wax guard. So if you have a hearing aid where the receiver or the miniature loudspeaker is sitting in the ear, you can see the CAD rendering here on the left. Then to protect the little microspeaker, you have a little insert which is called a wax guard. It's basically avoiding earwax to get into the system. And as you can see, I'm just jumping a bit between slides here. There's a zoom in here on the image. It includes a lot of very small holes. So these are like, I think it's 50 micrometers or something like that in diameter. So they're very small. And those actually, they protect from earwax, but they also change the acoustics of the system. So in this model, we are exploring the acoustic properties of such a wax guard, and then we are using it in a system simulation to compute the response of such a transducer located in actually one of these ear canal simulators. And the graph here shows a comparison between the measurements and then the simplified transfer matrix representation. So what we do is we take the wax guard, we make a very detailed model with the full thermoviscous equations. We have some conditions that are called acoustic port conditions. So you have one condition at one end, and then you solve the model. And out of that simulation, you actually get a transfer matrix representation of that this little system here. So you simplify, or you lump this complex geometry to a transfer matrix representation. And that transfer matrix is an automatic output from COMSOL. And then we use the transfer matrix in a transfer matrix system simulation to get these curves here. So another nice place where you can do this submodeling, so you can take a small detailed system and you can compute a transfer matrix representation, a two-port representation of that using some detailed simulations. Yeah.
There's actually another question about
yes.
This boundary condition, thermoviscous boundary condition.
Mm-hmm.
If that would work for higher frequencies, maybe above 3 kilohertz, when modeling these perforated plates, and
yes, I think so. Yeah.
So I guess it's a matter of if the boundary layers doesn't overlap, then you can actually use it for
yes, and
also.
The good part is the good part is also at the higher frequencies, the end correction actually will only have to do with the moving mass, and this part of that end correction is captured correctly with pressure acoustics. So you just get the losses applied near the wall where the losses are actually. So sure, for higher frequencies, if you have a perforated plate where the perforations are bigger, so or bigger.
So the first thing you always should do is to calculate the thickness of this viscous layer.
Yeah, and
then choose the right tool.
Yes, sure, too. And actually, when you solve a model, I think when you add, at least with thermoviscous, also acoustics, and also thing with boundary layer impedance, we actually have a post-processing variable for the thickness of the layer. So you can post-process that. Otherwise, it's a relatively simple expression, as you can see here. And there are some, I always remember it. So I remember that at 100 hertz, it's 0.2 millimeters. And I remember that it scales as 1 over the square root of the frequency. So if I remember the value at one frequency, it's easy to compute at another frequency. Then you don't even have to remember what, the expression here, viscosity and density and stuff like that. It's a trick we often use in the tutorial models. Yeah. And it's actually a good something that will be, so I will get back to this perforated plate model, and I'll look into computing looking at maybe a volume average, and then I'll actually also try to add boundary layer impedance at high frequencies. And there should be a match. I expect there should be a match between the models. And then you can actually start to see, you can run the boundary layer impedance model at lower frequencies where it's not valid anymore in theory, and then you can actually see when it starts to deviate a lot from the full model. So it's also maybe get a feeling for when you can use one and the other method. So it's a good suggestion. I will have a look at that also. Thanks. See, that's why it's so nice to get good questions. You also get some nice feedback and good ideas. Yeah, I've mentioned this, so you can couple thermoviscous acoustic to vibrating structures, and this is a model of a micromirror. It's a small MEMS construction that you use when you have, I think you use them in DVD players, Blu-ray players and stuff like that. And you want to understand when these small micromirrors, they start to vibrate and how damped the vibrations are. And this is and most of the damping actually comes from the little mirror being surrounded by viscous fluid. Yeah, so here are some links to some tutorial models and also a blog post if you want to look more into that. There's also this model of a piezoelectric MEMS speaker. So it's 4 triangular membranes that use a layer of piezoelectric material, and the membranes are actually, you can see, separated by a very thin gap here. Because the gap is so thin, the viscous forces in the gap are relatively high. So when the speaker moves, the membrane actually moves or the 4 triangles actually move as one membrane. So acoustically, they behave as a single membrane. And this model, this tutorial model, there's a link to it here. It's also in our inside of the software. And this model actually also uses thermoviscous acoustics in this little slit between the membranes, and then it uses the thermoviscous boundary layer impedance in other regions of the model. So it combines the two different models actually, or representations of these thermoviscous losses. Good. This is a very new tutorial model, so it's of a balanced armature transducer. And this is one of the small transducers that you use in hearing aids. It's not repeating here. And this is a new tutorial model that we actually released in December, I believe, when the new version of COMSOL was released. So it's not so much related to thermoviscous acoustics, but in the latest version of COMSOL, there's a new magnetomechanical forces multiphysics coupling that allow you to actually set up a multiphysics model of this transducer relatively easily. So this model includes a coil domain. So you have an AC electric field that generates an AC magnetic field. You have a permanent magnet here that generates a DC field. You have a structure here which is made of a magnetic steel, which makes a magnetic circuit. And the interaction of the DC and AC field makes this armature move and makes the rod move, which makes the membrane move up here. And you have a very thin layer of air here, so you need thermoviscous losses, and that generates a signal that comes out of the spout of the transducer here. And also this model consists of two models. It's also using this sub-modeling idea. So the measurement system attached to the end here is actually modeled with the transfer matrix that we compute from a larger system. So I highly recommend you take a look at these two tutorial models. They're very nice. And again, some more balanced armature transducer models here. They are coupled to a test setup with a piece of ear mold tubing, and there's a coupler volume. And this model actually looks at the vibrations and the acoustics of the transducer. And this is the measurement setup of the actual system. So the little receiver, the ear mold tubing, you have a laser that measures the vibrations. You have the coupler volume, you have a measurement microphone, and then this is a tutorial model where we compare simulation and measurements, and there's a very good agreement here. And this is also a nice model we've made in collaboration with Knowles Electronics. So yeah, good. I'm getting to the end, I think. So this tour is actually the slide we should have had in the beginning, where you asked this question about lumping. So this is the piece of a muffler where you do a submodel of the perforations. You compute the transfer impedance that you apply as a boundary condition in your model. Yeah. Microphones, we've talked about those, but I just want to mention something nice is that if you have a microphone, then you can, and you are using thermoviscous acoustics, then you can actually compute the equivalent, because you can compute the losses in the system. You can compute the equivalent acoustic resistivity or resistivity in the model. And from that, you can, using this Johnson-Nyquist model, actually compute the thermal noise of your microphone. And in this case, you should think of thermal noise not as having to do with temperature so much, but to having to do to heating due to viscous and thermal dissipation. So that's why you call it thermal noise. It's not only due to the temperature fluctuations, but it's due to the dissipation of energy in your microphone. So this is described in our, so we have a model of a BK4134 condenser microphone. This is where the image is also from. And there are some links here to a lot of microphone models. Good. So in the beginning, I showed you, so I think this is what I wanted to say about linear or multiphysics models and linear thermoviscous acoustics. And then in the end here, I have a few slides of some nonlinear effects also I know they're much more advanced applications, but things you can actually model and you can actually gain some insight into. Are there any questions, Ture, before I proceed?
Maybe one thing. I don't know if it is something you want to go too much into now, but if you want to make these models extremely accurate, air is no longer air. So
yes,
that's something to touch.
Yes, yeah, sure. So of course, when these models depend on the material properties, and you need an extended array of material properties. Let's go in here and so you see you need to enter speed of sound, heat capacity, ratio of specific heats, thermal conductivity, dynamic viscosity. So this is for the narrow region acoustics model here. And those depend, of course, on the background temperature. They depend on the background pressure. So is it 20 degrees in your room or 25? But they also depend on the humidity in your environment. And actually also, if you really want to go into details about the composition of the air. So is there more or less CO2 maybe in the air? Are you working with a special environment? Like maybe you have a closed cavity with some special gas in it. And we can actually, I just want to mention this, in COMSOL we have something called the thermodynamics of the liquid and gas module that adds functionality to COMSOL, where you can compute the material properties from first principles, including temperature, pressure, relative humidity, and also composition of the air. So if you know these things, you can actually get very accurate and very good values for the material properties. And if it's something you want to look at, I recommend you take a look at, we have a model of a pressure reciprocity calibration coupler that is used to calibrate microphones. And this model actually shows how you use this liquid and gas properties or thermodynamics functionalities to set up moist air in your model. So it's actually quite interesting because we had a long, maybe some years ago, we had a long, I was fighting with some standards here and there, and it was very difficult to actually get IP rights to implement or add detailed properties of air because, of all some kind of legal issues. But then we had this thermodynamics functionality that was being developed. And I heard about it from one of my colleagues in Stockholm. And he said, well, we can model moist air. And then working with them, they actually made functionality. So it's super easy. So you can just write and then set up a predefined system where you can select dry air, moist air, or water steam mixtures. So we have built in some of these thermodynamic systems for some of the most common uses. So you can set up moist air really quickly, and then you get, I'm talking a bit about it, but I think we have time. Then you can compute the dynamic viscosity as function of temperature and relative humidity with great detail, great precision. So
it's not something you do in your average first model, or
no.
It's when you're really fighting details.
Yeah.
Then there's another question about boundary conditions or boundary simplifications for this 3D compression dryer with structural couplings. I think we need a little more information from the one who asked. So if you can elaborate a little, then we'll come back to that question.
Yeah, definitely. So I will go quickly over this. So I want to talk a bit about, this is some new functionality we added a year ago. So now we are moving to the time domain because we want to capture nonlinear effects. So those are effects you typically see in miniature loudspeaker ports, in perforated plates operated at high sound pressure levels, in grills, meshes. So you can compute the edited or the nonlinear resistive losses, and you can also compute distortion due to when a nonlinear effect is going on. I think I mentioned this, you get some distortion also going on, vortex shedding. So the image of to the right here is the mobile device again, where you can actually see that when the air is moving in and out of the port because it's emitting sound, you actually get some small vortices generated. So a much more classical example is again back to our favorite perforated plate. So this is a model of a perforated plate, but what we see here is now that it becomes level dependent. So maybe the graph here is not that good. I have a better graph. I'm sorry. I think it's the wrong slide. But anyways, there's we have a model that you can download where we actually compare. So this is okay. Let me start from the beginning. This graph here shows the transfer impedance as function of frequency, and the full line here is modeled with in the frequency domain. So linear acoustics, the circles are modeled with the time domain model, but not including the nonlinear effects. So we see that the time domain and the frequency domain models agree. The dashed line here is the analytical model, and the red dotted points here are the actual transfer impedance, including the nonlinear effects. So the additional losses, because when you can generate these vortices, you also generate some gradients in the flow outside of the hole, which generates some extra losses. And this curve here, these values are actually validated looking at a research paper. So the values are correct. So this was the question, if you can compute the level dependent transmission loss. So depending on the amplitude of the incident wave on the perforate, these values will lie in different locations. So as you increase the incident level, the transmission loss will actually increase, but the transfer impedance, the absolute value of the transfer impedance. And you can see it's also frequency dependent. So there's an interplay now between frequency, level, and geometry. Final nonlinear effects I want to mention. So this is a nonlinear effect not due to the generation of vortices, but if you have a moving, so you should be able to see it's an animation to the right here. You have a membrane that is moving close to a backplate, and when the gap becomes smaller, you actually have more losses than when the gap is large, because the boundary layers make out a larger or a smaller part of the gap. So what you get is something called nonlinear thin film damping. So here the nonlinearity is not coming from large amplitudes, but it's coming from a change in the geometry. And you can see this. So the system is being excited by a single frequency, but you can see when you look at the response of the system, you get higher harmonics generated. So yeah.
And this is also only in time domain you can capture these effects, right?
Yes, yes. Good. I think I'm at my second to last slide. This was actually the slide that shows you the setup of the model of the animation I showed you in the beginning. I'll show the animation here at the end again. So the system is that of this system is taken from research paper where there are some measurements that we validate or that validate our simulation. So you have a resonating volume, you have a long pipe, and then you have a very thin slit. So the slit is exaggerated in size here. Then you're sending in a wave that interacts with the slit and the resonator volume, and you have a reflected wave. And then in this model, we compute the reflection coefficient as function of frequency. And what you'll see now is a zoom close to the little slit, and this is the animation I showed you in the beginning. So you actually get some very strong nonlinear effects going on. And what we this is actually in the order of several degrees C fluctuations. So the air is actually getting hotter and colder by several degrees when this acoustic wave is interacting with the small slit. It's mesmerizing. It's you say it looks like a lava lamp, right?
Yeah.
Yeah.
You can almost fall asleep and look just staring at us.
Yeah. Yeah, I think it's maybe good to end now. So yeah, I hope I wanted to make it clear that you should, of course, include these microacoustic effects, the thermoviscous losses, because if you want to get the correct behavior of your systems, we offer a variety of tools to do that, and also tools that are fast and efficient, and some that are more detailed, etc. And I hope you understand. I mean, my point was also that you can actually model these things, so you don't need to guess where does the losses come from, or how will the damping be in my system if I change the geometry. You can predict all this, and you can predict it with very high precision.
And that's while you're here, and before we go on to the workshop part, since we have so many users, I'm not sure how many people are going to stay for the workshop, because we're going through really basic use of console for this. So if you have questions now that we have Masser about something, maybe you should ask them now instead of during the workshop, if you have any usability questions of a more advanced nature.
Yeah, I have console ready here, so.
Now, I'd just like to mention that you can also, we can unmute your microphones. You can also speak directly to each other. If you just raise your hand or write a question in the Q&A, we can unmute your microphone. Sometimes it's easier.
Yeah, so just raise hands if you have any questions. When we go through the workshop parts, we will just build this 711 coupler with narrow region acoustics, but we will focus a lot on how to use console multiphysics. So it's meant for rather new users of the software.
Yeah. Would you already like to check who will join for the workshop and who already has the software?
Yeah. Maybe we should. People will stay if they want to participate in the workshop that we will start, I think, in 5 minutes time or so. But if you want to stay and you have a console installed, then please raise your hand, because then I know if it should be a workshop or more like a demo where I just build the model.
And also, yeah, I want to reiterate, if you see or have seen any of the models that you cannot find, please contact us. We can send you the model, or we can find it for you. And also, if you have other questions, please get in touch with us. Yeah. Okay,
we have another question that I don't know, but can you go directly for Viscous losses to BEM? No, or do you need some kind of FEM in between, pressure acoustics in between?
That's a good question. I think we can couple directly, but I can check.
But,
yeah.
Yeah.
I think we can, but I'm pretty. Here we got them. So this is something we've not talked about, is the numerical methods that we use, but we have several of those. So let's Thermoviscous acoustics. And oh, yes, they are coupled together now. So yes.
Yeah, so it's already a predefined coupling, so you don't have to worry too much about it.
Yeah. Yeah. So one thing you need to be aware of, yeah, I don't know for the person that asked, but it's always good to have if you have a wall in common between the pressure acoustics, either boundary elements or fine elements, and the thermoviscous acoustics. Sorry, this may be a bit technical. If it's an outer wall, say you have a waveguide that comes out to the outside world, then I recommend you have the outside wall, and you on the wall you add an extra wall feature, and you select slip an adiabatic here, because then the physics that are coupled together will be complying, because otherwise you have a boundary layer that suddenly ends where there's no boundary layer, and you can it can end up introducing some small numerical errors. Typically not very important, but it's a good practice to have physics that are compatible when you couple them. Yeah.
Great.
Good.
I'll leave you, and then I will start the workshop at 2:45, and give you a chance to just get up a bit, and then we'll carry on.
Absorb all of that information.
Yeah. And then we will carry on from 2:45.
Yeah, great. Thank you all for listening.
Thank you very much, Mads.
Thank you, Shelley. I will make sure you'll be the presenter soon.
Yeah, and for anyone who is not going to stay for the workshop, thank you very much for taking part today. We will send the slides and some links afterwards, and the recording will also be available. So if you have any colleagues who couldn't make it, or you're in a time zone that meant that it was too early for you to join, then you can access it afterwards. Yeah, and keep an eye out for our upcoming events. Almost all of them are free to attend, all of the webinars anyways, so you can sign up to the newsletter and stay in touch that way and hear about the upcoming ones in the coming months. So thanks everyone, and we'll see you back in how many minutes? 6 minutes for the workshop.
Yes.
Bye-bye.
Thanks. Bye.
Mads, are you still here?
Ja, jeg er her, hvis du har brug for noget. Men det kan godt være, at det er Mads, som skal hjælpe dig.
Ja, det var lige et spørgsmål, som jeg ikke umiddelbart kan svare på, men det kan være, at Mads han kommer tilbage, så tager vi det, når han er her. Ellers så går vi bare stille og roligt i gang med almindelig workshop.
Mm-hmm.
In a few minutes.
Yes. We still have most of our audience here.
Yeah. I'll just get started. Before I start to figure out if we are going to do this as an actual hands-on workshop or if it's more like a demo from my side, there is somewhere in Zoom a possibility of raising your hand. So if you have console installed and want to follow what I'm doing, can you raise your hand? Otherwise, I will just do it as a demo. So it's probably going to be more like a demo thing. Good. Otherwise, just let me know also if you have questions about the general use of console. The more in-depth acoustic questions we will have to refer to Mads, but I will take questions about general use of console. So the model that we're going to do is the 711 coupler that Mads talked about that emulates part of the ear and looks something like this. And we will actually model this both with and without these viscous losses in these slits to see the difference and see how you can build up the model one step at a time in order to capture the effects that are necessary for correct result. When I run this demo, it's nice to know a little bit about how the user interface works and how it looks. This is console as it is, and the most important part is part over here that is called the model builder, and this is a tree-like structure, and that model that tree is the model, and it is actually when you start to learn to use this tree, it is also a complete description on how the model was built. So when you see a tree, you immediately know how it was built. And you can consider some of these nodes, like the geometry node or the mesh node and so on, like small scripts. So they are run from top to bottom, so you can move things around, and it would actually change the behavior of this particular node. Whenever you click a node, there are some settings here that you can set for that particular node. And very often there's a button up here in the settings window. In this case, it's a plot button, but it could be a build geometry button or build mesh button or compute button, but there are some contextual buttons in the settings window. Nice to have is of course the graphical representation. It's not so much need to have actually, but it's nice to have. And at the bottom, you will get numerical outputs and all kinds of log and progress information and messages goes on here. To the far right, sometimes you have different kinds of libraries, like material libraries or libraries of more physics or things you want to add. But these are just libraries. So if they have to play a role in your model, they need to go into the model builder tree to the left. And the last thing you normally see is the ribbon up here. And the ribbon kind of gives you an idea about also the most normal modeling process. First, you set up some definitions, then you have a geometry, you apply materials, you set up the physics, you mesh the geometry, you solve it under study, and you post-process it under results. But you can see this is just a vertical description of the tree where you have geometry, material, physics, mesh, studies, and results. And just before we get started with the actual model that we're going to build in a little more details, I just built this model very fast because it actually includes all the things that you usually want to do when building a model. It's a very simple model. It's a large cylinder where where I have a normal displacement at the bottom, and I'll solve it from 100 to 500 hertz. Yeah, and I'm going pretty fast through this and more details through the 711 coupler when we come to that. So if I start console, it will look something like this. And what you usually do is you start a new model using the model wizard, and you can work in 1, 2, or 3 dimensions and axisymmetric models. Quite useful for loudspeakers often. But in this case, I just start a 3D model. And then you need to select what physics to include. And it can actually be quite cumbersome. So I'll show you where in the documentation you have a short description of all the different physics, so you can choose the right one. But for simple pressure acoustics, we start with this pressure acoustics frequency domain, which would be a finite element version of it, but there's also a boundary element version of it and a transient version of it. So I press add, so you can see I have pressure acoustics, and I'm solving for the acoustic pressure, and it's called P, so the dependent variable is pressure. Then I press the study button, and I will do a frequency domain study, but you can do other kinds of studies also. Press done, and then I'm in the model. So you can see I have a 3D drawing board, I have the pressure acoustics, and I have a frequency domain study step here. To begin with, I want to define some parameters. You can think of parameters like constants in your model. It could be that I want the normal displacement that I had at the bottom. We have 1 micrometer of that. So type in stuff with units, because then you also have a unit checker in your model when you type in stuff in your boundary conditions and so on. It's checked for being of the right unit. So these are the ones that I'm going to use. Maybe I also want the radius for the cylinder. So now I can start building my model, and there's many ways of working with COMSOL. If I want to do something with geometry, I go to the geometry node here. And if I'm working with something in millimeter scale or micrometer scale, remember to change the unit here, because all the tolerances in your geometry, or whatever it be in something imported from a CAD tool, all the tolerances are absolute, but relative to the length scale anyway. So remember to set this correctly, so it fits your model. Then there's two main way of operating COMSOL. Either right-clicking here. So here is what I can do with geometry at this point, or click the geometry tab up here, and then see I want a cylinder. Then you click the cylinder, and it pops up as a node in the tree here. And there are some settings for it, and I have a radius that I want to change, and then I can build my geometry. Often it's something that is imported from a CAD tool. Then I want to add materials to it, and you click this material button and right-click it and add material from library. It's typically what you want to do. If you have a material that is not in the library, then you start from a blank material and define it yourself. But for now, I actually want to just add it from the library, and you can see over here I have a bunch of libraries. One of them is called built-in, which is the one that we are going to use today. there's air, so I right-click air and press Add to Component. So you can see I'm used to right-clicking, but you can use the buttons also here and there. So now we see air is in domain number 1. We only have one domain, so it's simple in this case. If we then look at the physics interface, it's called Pressure Acoustics Frequency Domain. And what it actually does is this icon is a domain icon. So we are going to calculate pressure acoustics inside this cylinder. Of course, we need to say how the surrounding interacts with this, and that is boundary conditions, and that is this icon here. And by default, all walls in pressure acoustics has sound hard wall. And if you want to know more about what it actually is, then you can read in the documentation, or you can see the equation here. If you have help running, then this help, then you will have a description of whatever node you click. You will have a description of that to the right, or wherever you place your documentation. So the only thing I want to change in this model is actually the boundary condition on the bottom surface here. And again, there's two ways you can operate it. You can either just right-click the tree, and all the domain conditions that you can add to your model is up here, and all the boundary conditions you can add to your model is down here. But another way of doing it is to click the physics up under on the ribbon, and then you can see boundaries, and I can unfold that. And then there's a bunch of different kind of boundaries, and one of them is called normal displacement, and that's the one that I'm interested in. So, and then I have a node in the tree, normal displacement, and I click the boundary, and then I put in the parameter G0. And then I'm basically done setting up the physics. I don't want to just mesh the thing yet, because I'm going to use something that is called physics controlled mesh, which is new in 6.0. So for pressure acoustics, you can actually let the physics control the mesh. But in order to control the mesh correctly, it needs to know the frequency. So I need to specify what frequencies I want to solve for. So I'm clicking the study step here. And then I can type in the frequencies, or I can use this nice range builder icon here. And I can have stop, start, stop, step, or whatever. But often in acoustics, you have these ISO preferred frequencies, where I start at F mean, which was 100 Hertz, and go on to F max, which was 500 Hertz. And then how many frequencies I want in an octave. And I can just go with a very fine resolution of 1/24. And press replace, and then you can see what frequencies is actually solved for here. Now, when I go to the mesh, it takes the largest frequency and makes sure that the mesh can actually capture that, and that can be done with this mesh. And just to show you that if I change the largest frequency all the way to the end here, I've put in 5,000 instead, for instance, then the mesh needs to be much finer in order to capture this frequency or the waves, because you need at least 5 to 6 elements per wavelength, and you can see it immediately makes sure that the mesh can capture that. Let me just get rid of that again. So, and we're back to the more coarse mesh now, and we will solve this for all these frequencies and take a look at some output. So whenever you solve a model, you get some default plots. In this case, you get the acoustic pressure for the different frequencies, going to 100 Hertz, and then I can, with the arrow, step through the frequencies and see what happens. There's also a sound pressure level plot and acoustic pressure isosurface plot. What I would like to plot is the average acoustic pressure on the top here for different frequencies. But that's a 1D plot, it's a line plot. So I create a new plot group, right click this one, create a new plot group. The plot group that is just a container, it doesn't do anything by itself. So I'm going to right click that. And then I'm under more plots, I can find something called an octet band plot, where I can select a point that's not what I'm interested in. I'm interested in domain boundary, so I can select this boundary here, and that will take the average pressure, total acoustic pressure, and plot it in over some octave band. But that's, again, I would like just a continuous line, so continuous power spectral density in this case, and hit plot, and we can see the resonance frequencies showing up here. So this is, I'll just give myself a little more space here. So this is, this model actually includes more or less what all models, what it takes to build any kind of model. You set up a geometry, you apply materials. In acoustics, it's very often air. You change some boundary conditions and maybe some domain conditions. You measure it, you set up the frequency range, and then you plot it. A few things that is relevant when you solve it. When you solve such a model, what you in reality gets is a data set. So the data set here is actually holding the solution. So when I do a 1D plot, the plot group tells me what data set to use. So if you have more data sets, then you can choose which one to actually post-process in this case. And you can see it's the same thing for the 3D plot groups. It actually works with some kind of data set here that you can change if you have more than one. If you want to compare a frequency model with a time-dependent model, then you will have a study 2 that is a time-dependent model, and you can compare it by selecting the right data set afterwards. Okay, any questions? It's probably best if you just ask questions as you go along. It can be any kind of questions. Okay, if no questions, let's move on to actually modeling this one. A few things about this. There are some dimensions. We don't want to draw it. We just want to import a CAD drawing. But there's some dimensions on the main cylinder, but especially the slit heights are pretty narrow, as Mads mentioned. It's around 70 micrometers, the height of these two thin slits here. So that implies that we might want to include these thermoviscous losses. But to begin with, we will just solve it with plain pressure acoustics. But we need some more information about boundary conditions for the conditions for the microphone and for the inlet up here. So what do we want to do? The inward, we have a normal displacement with a specific normal displacement amplitude. And then the microphone, we will use a lumped version of it that corresponds to this 4192 Brilliant Care microphone. So we just need to choose the right values for these. And I will show you in a second how to do that. But this is what we need in order to actually start the model. And it can be a good idea to when we start this model, let's start a new model here. New model, model wizard, 3D model, definitely. Pressure acoustics, just as before. Again, if anyone wants to follow what I'm doing, then let me know. Otherwise, I will just go forward and you can ask questions as I'm going through this. So again, we have pressure acoustics. We are solving for the acoustic pressure P. Next, we're working in the frequency domain. Done. The geometry. It's a relatively small thing, so I'm going to go in millimeter scale, and then I'm going to import the geometry. So this can be any CAD file format that you can come up with, and we can talk more about how to work with your CAD models, because if you have complicated CAD drawings, they might not be really suitable for simulations, but you can do some work on them so they actually work anyway. I'm going to browse to it. So when you are following step-by-step instruction yourself later on and are going to being asked to import something, then I just want to show you where they are. all files are wherever you install console. C program files, console 6.0, multiphysics, applications, and then in the acoustics module. And then it depends on what kind of model you have. This model that I'm building is actually a tutorial model that are in the Thermoviscous Acoustics folder. So here I have, for instance, parameters, so I don't have to type them in myself. And I also have the geometry, as you can see here. So that's what I'm going to do now. I'm browsing my way all the way, program files, console 6.0, physics, applications, acoustics module, and then I have the application library. I'll show you the application library later. I have the same structure here, and I'm going to tutorial Thermoviscous Acoustics, double click, and I'm going to take this generic 711 coupler MPH bin, which is our CAD format, but you can choose any CAD format that you want. And then we can see it here. So the next thing we want to do with this model is to apply materials. And it's important to understand that what is drawn here is not the coupler, it is the air inside the coupler. So the only material we have is air. So I right click, add material from library. I go to build in, and then I apply air. So now all 6 domains are air, and what 6 domains are that? It's this one, and the slits. They are separate domains for a good reason, because later on we want to apply some special conditions for these slit domains. But for now we will just leave them as they are. You can see by default all walls are sound hard wall. Now this is only half a 711 coupler, so we should have a symmetry on these conditions, on these boundaries, but I don't have to set that up because sound hard wall and symmetry is basically the same. But if you want to send it to someone else, you might want to add a symmetry plane and just explicitly say that this is symmetric. But for now, I'll just leave it as it is. But I do have on the top, I have this normal displacement. I have right now just right click on the pressure acoustic. So I take this normal displacement, and then I click this. You can see it turns red when I hover over it, and then I click, then it's blue, and that means that it is this boundary number 19 now has this normal displacement on it. If I chose the wrong one, I can hover over it again, then it turns green. When I click, it is unselected. So those are the colors that you use. I don't exactly know what this should be, so I'm going to parameters, and then I'm going to import some parameters. And they are placed in the same folder, and they're called coupler parameters. Open, and you can see I have F max, I have the lumped, the value for the lumped components, and I'll also have the input source displacement, D0. So I go back to my normal displacement and put in D0 here. Then I have the microphone at the bottom, and that was kind of a lumped impedance model. So instead of right-clicking, I might as well go to physics up here. It's the same thing, boundaries, and then I have an impedance boundary condition. So here you can type in your own impedance, or you can get a little help by choosing one of these. Of interest to many of you might be the physiological impedance models, where you can have human skin, outward human ear radiation, human eardrum, human ear with piano, and human ear full. And again, if you select something, you'll get a small sketch on what it is, but you will also see the equation up here that you can also find in the manual with reference. But for now, we need an RCL, and you have different things to choose from here. I choose this serial coupling. Mic was one of parameters that I imported, C mic and L mic. So now I just need to say, where do I have this microphone? And I have it here in the bottom. So that's boundary number 17. Now has this. All other, so we have at the bottom here, we have an impedance representing the microphone. On the top, we have the inlets with an inward displacement. And all other boundaries are now sound hardware. You can see these up, this one and this one here is no longer highlighted in blue. So those are no longer sound hardware. So that's the default one. Again, it shows you a very important thing about Consul is that you override stuff as you go down in these nodes, which is extremely nice when you work with it. So the last thing we need to set up is the frequency domain, or the frequency where we want to solve this. And we want to do that before we measure it, because again, it is physics controlled meshing. So I click this one and I click this one, and I want to solve it from 100 Hertz to, oops, sorry. We definitely want to use the ISO preferred frequencies from 100 Hertz to 25 kilohertz. And maybe in this case, we only want 1/6 octave. Otherwise it will take a very long time if we have too many frequencies. And now we can build the mesh. And you can see that it is more the geometry than it is the frequency that actually controls the mesh size right now. We will come back to meshing a little bit more in details later, because this is probably, or definitely not a mesh that is going to capture all effects if you have thermoviscous in these. But let's compute so we can see what is happening with this one. So now it's just solving the model, which is, and here you see the results for 25 kilohertz, and you can see the results for the acoustic pressure for the different frequencies. You can see the sound pressure level and so on. And then now you can start to do a little more elaborate post-processing, but I will just do as we did before, look at the average pressure at the microphone, so we get some kind of idea about how this acts. So I right-click, I create a 1D plot group. Again, we only have one study for now, so we only have one data set, so it's easy. I right-click under more plots, I find this octave band thing, and I can change, instead of measuring a point, I'm going to measure the average on a boundary, the microphone boundary. And again, just as before, I want to do it in a continuous power spectral density plot. And we have something like this, which is not expected. I probably have something, yeah. So now I'm going to do something that I shouldn't do, but I think I have messed up the dimensions in my model here. Probably came too small. It became too small because I put it to millimeters, and then I imported something that was in millimeters, and millimeters times millimeters is going to be micrometers, as you can see. So if I go back to millimeters and then I scale, build all, scale back to meters, build all. So now we have something that is way too small. So let me just skip this model and open a model where I have done exactly the same. No difference, except that I'm going to plot this is the output on this boundary 17 here, where I'm looking at the average pressure. So in building these models, you can just, I'll just again let's get rid of that one. So you can see how that interacts. I'm going back to the other model, even though it's wrong, just to show you how to add narrow region acoustics to it, because this plot here is not correct, because it's without the damping in these narrow slits here. So let's take a look at how these can be incorporated into the model. You could add thermoviscous acoustics to the model and solve that, but for now we will just show these narrow region acoustics. And again, I can do it here, or I can click the physics tab and have a domain condition that is called narrow region acoustics, and then I'll just select this one. This is an analytical expression, so we need to tell it what kind of slit it is, and this is a rectangular duct. It looks more like a rectangular duct, and then we can say something about the size of it in order to set up the correct analytical expression. And again, here you can see it's a good idea to type stuff in with units instead of setting up 10⁻⁶ and things. So that was that slit. The two other slits, the one that is hiding here and the one here, they're more like slits. So I'm going to go to domain conditions, narrow region acoustics. I'm going to select this and this, and these are more like a slit condition. And then I just need to apply the height, which is 69 micrometers. So, and now I can mesh it and solve it again, and I will see a different response. If I want to compare my two different models, one with and one without the narrow region acoustics, I might actually just add another study by right-clicking the top one, add study, add a frequency domain study. And now I can copy paste the frequencies that I'm using in one study, copying them to this study, and then I can solve it again. And now I'll solve it with narrow region acoustics, and that's what I have done in the other model here. You can see that I have two studies, and now I can plot both with and without narrow region acoustics. So without, we get the green one, and with, we get the blue one. So we can see for the lower frequencies, it actually has an impact adding these narrow region acoustics. For this model to work, then you can, if I don't do anything, both studies will solve the full model, but I can actually go into a specific study step. Here we include everything in the model. In this one, I actually click modify configuration, and then I have disabled these two conditions. So when I solve study 2, it's always going to be without narrow region acoustics, and when I solve study 1, it's going to be with narrow region acoustics. So it's easy to compare. The only thing is that I then have two study steps or two data sets. So when I go in for acoustic pressure, right now I'm looking at the one with narrow region acoustics. Now I'm going to look at the one without narrow region acoustics. So I need to be careful about this. Okay, if we take this model one step further, we can do that in the application library. And this is what I really want to stress, that when you are on your own in a second, you can go to the acoustics module in the application library, and you can go down to thermal tutorials, Thermoviscous Acoustics, click the generic coupler, press this open PDF document, and then you will have a description first of what we are solving. And it's a quite elaborate description in this case, so I'm moving fast forward. And then a discussion of the results. But if you are patient and you go all the way to this point, you will have exact description on how to build it. In the new window, click the model wizard. In the model wizard, click the 3D button, and so on and so forth. And you will be handheld in setting up the model. And I recommend that you build a few of these models. And when you have done it, you start to get the grip of it. Then you can just open the model and see what is going on inside. And this model is comparing a full thermoviscous acoustics model with narrow region acoustics and with only pressure acoustics. So it actually has 3 solvers in it. You can see I have thermoviscous acoustics in only the slits, and then I have pressure acoustics in the rest. And then in multiphysics, I can couple the 2, pressure acoustics and viscous acoustics. But when you have this thermoviscous acoustics, you have to think a little bit about the meshing, because it's something that goes on the boundaries, close to the boundaries in these. So you want to make sure that you have more than one element in this. And you can see in this model, we actually have 3 elements across here. And you can do that if I unfold this by saying that to begin with, I only built a boundary layer mesh, which is a map mesh. And then I sweep that through the thickness here, giving it 3 elements, or how many elements you think is appropriate. Now I have meshed just the slit here. And then I say the rest go free tetrahedral. Just make sure that you obey 6 elements per wavelength. And then I have my mesh. So these swept meshes can be quite helpful when you're working with these narrow region stuff. And then in this model, there's since it's a tutorial model, there's a lot of post-processing going on. So you can look at the transfer impedance. The standards is the red line with the band around it. So you have to fall within this in order to obey the standard, and the 711 coupler does so. If I zoom in, you can see that I have this purple dotted line is pressure acoustics, and it falls completely out. Then I have the full thermoviscous acoustic model, which is the blue line. And then the narrow region acoustics model, which is the green line, the one that we just set up. And you can see the difference here is so small. So the narrow region acoustics is actually in this case capturing the losses in the model pretty well. And it's somewhat faster than solving for everything. It's 38 seconds in this case, and 1 minute in the other for the full thermoviscous model. But for larger models, there's a difference. So it might be a good idea using narrow region acoustics where possible. But this is a nice tutorial model. Yeah, this is the narrow region acoustics setup. So if you calculate this viscous layer or in the thermal layer, you can see that from 100 to 20 kilohertz in air, it goes from 22 micrometers to 15 micrometers, and that is comparable with the size of the slits. So now you have to do something about the losses in these slits. So when you start to model on your own, I will, and you haven't used COMSOL before, I really strongly recommend going to the documentation. And just wait a second until it starts up. It takes a little while. Because in the documentation, you have these introduction to booklets. So over here, you can see that you have the acoustics module introduction, and click the PDF. This is a nice booklet to actually read almost from one end to the other. It doesn't take that long, but it have the contents, of course. But it gives you an introduction to what you can do with the acoustics module and the different methods that are here. And it's rather condensed, so it's easy to read. And then it gives you an overview actually of the different physics interfaces. And this is a pretty good idea to start with. Just read this. It doesn't take that long. And then it has a an example model. If I click this, some basic acoustics, and it's again, it's good to read. So, and here you will model a muffler in this case, but it will guide you very, very slowly through all of it. So when I go down to the step-by-step instructions that are coming here, you will be guided very, very slowly through the whole process of setting up these models. And that's pretty, and in that way, you learn to use the software pretty fast. And then when you have built that model, you go to the application library under the file menu and find whatever model you think is nice. In order to get all the newest models, remember when you open the application library to click this update console application library. So you get all the newest models, and then use the PDF for instructions and just open the model if you want to figure out what is going on inside. That was what I had for now. What we have been going through today is the acoustics module just for licensing purposes, but you can couple it with things from the AC/DC and the structural mechanics module if you're doing loudspeaker microphones. If you have nonlinear structural materials, or if you have composite materials, you can couple it with all here and there as you need. And for those of you who know a little bit about COMSOL, the uncertainty quantification module is a new module where you can quantify uncertainties. So if you have production uncertainties, you can see how that actually influences your model in a very intelligent way. Yeah, that was all from me, unless you have some questions. And if not, call us. Remember, you got a link from Shelley where you can actually download a trial of the software and test it out for the next 14 days, and just send the questions to support. Then we will most definitely help you with getting started with using the software. And I can see there's questions about the discretization order, and usually for the thermoviscous model, I'm not exactly sure about this, but usually if you change the discretization order to something smaller than what is default, the mesh has to be much finer. Usually we say that the default that we have is a rather good compromise. And what am I talking about? The thermoviscous acoustics here. The discretization can be set here, and you can see that the element order for pressure is linear, and the velocity is quadratic, and for temperature is quadratic. And changing these, you can change these. You probably just have to be careful, and I'm not exactly sure. So if you need a more thorough explanation, please ask support. Then I'll ask Mads to send you the more detailed description explanation on how to select the discretization. Okay.
Thank you very much.
Thank you. Hope to see you.
Have we lost Mads? Have we lost Mads forever?
Yeah, I think he's
gone.
He got a questions that triggered his development mind, so he's looking into it.
Excellent. Well, thanks again for being here today, and yeah, we will share your contact information as well in the follow-up email.
Perfect. Yeah, great. Thanks a lot then.
Thank you, and thanks to everyone out there for listening in. Bye for today.
Bye.
Bye.